this alkene is more stable than the alkene that we started with. In this video, we're going to discuss the radical allylic halogenation reaction. As we begin this reaction, recall that radicals, like carbocations, can be stabilized by resonance. The radical allylic halogenation reaction is a reaction of an alkene. Specifically, though, it's the sp3 hybridized carbon next to the alkene. That carbon next to an alkene has a name. We call that carbon the allylic carbon. The allylic carbon is the name we give a carbon next to an alkene. The hydrogen on that carbon then is the allylic hydrogen. So we call this the radical allylic halogenation because we are replacing that allylic hydrogen with a bromine. The reagents for this are a reagent we abbreviate NBS, and we need light or heat energy to initiate this reaction. Let's take a look at some notes for this reaction. This is a radical mechanism, so it does go through our IPT mechanism. NBS is an abbreviation, stands for N-bromosuccinimide, and the structure of N-bromosuccinimide is shown here. This reaction works for NBS, but it also works for NCS. NCS is the chlorine version of N-bromosuccinimide. So it would be N-chlorosuccinimide. And one point that we'll talk about briefly in this video, and then I'm going to have a separate video on, is when there are two constitutional isomer products possible, the alkene stability of those products determines which one will be the major product. That will be best explained as we go through an example. So let's go ahead and go through an example. We'll do an example where we have some kind of alkene starting material, and we are reacting this with NBS in the presence of light or heat. We'll do light. I'll save the product and we'll put the product here as we get through the mechanism. We start with the initiation. The initiation for a radical process targets the weakest bond. The weakest bond to undergo homolytic cleavage is often the heteroatom bond, a bromine-bromine bond, an oxygen-oxygen bond, or a nitrogen-bromine bond. So we'll start with NBS, and we'll do a homolytic bond cleavage, breaking the nitrogen-bromine bond. That will form a nitrogen radical, and most importantly, our key propagating radical, the bromine radical. This then takes us to our propagation sequence. In the propagation sequence, we will start with our alkene and the bromine radical. The bromine radical here will abstract a hydrogen from the allylic carbon. We're going to form a hydrogen-bromine bond. We need 2 electrons for that bond. We can get 1 electron from the Br dot, 1 electron from the carbon-hydrogen bond. There are 2 electrons in that bond. We need to account for both electrons. The other electron will get deposited onto that carbon as a carbon radical. So we will form a allylic carbon radical and HBr byproduct. What's important to note about this radical, this carbon radical, is that it can be resonance stabilized. So we have a resonance contributor for this radical. That's propagation step A. Propagation step B starts with this carbon radical that is resonance stabilized, and we react with Br2. We're going to use a carbon radical to abstract a bromine from Br2. Just hang on, I'll talk about it in a second. And we have 2 resonance contributors that we could choose from to do this bromine atom abstraction. The one that we are going to choose is the primary radical, the less substituted radical. We'll get 1 electron from carbon, 1 electron from the bromine-bromine bond. The other electron will go on to bromine to form more Br dot, and we form our product and more Br dot to continue the chain reaction. This Br dot can start another propagation sequence, which can go through and start another propagation sequence, and we form the bulk of our product in the propagation steps. A lot to talk about here. I'm going to focus really a second video on this whole process. Where does Br2 come from? Why do we use the less stable resonance contributor? We'll get to all of that. Finally, we have the termination steps. I'm a bit out of room on the board, so I'm not going to show them here, but we have all of our traditional termination steps: bromine, Br dot and Br dot, Br dot and carbon dot, carbon dot and carbon dot. Notice we also have a new nitrogen radical, so that can also do some termination steps. We can get a termination between N dot and bromine dot, N dot and carbon dot, N dot and N dot. We can have all sorts of termination steps. We'd have 3 radicals in this system. So this is the overall overview of this reaction. Our product is going to be an allylic bromide, where the bromine is on the allylic carbon relative to the alkene. Notice though that the alkene has now shifted to an internal position. This alkene is more stable than the alkene that we started with, and our byproduct for this reaction is HBr. This is an overview of the radical allylic halogenation. This is our summary card for the radical allylic halogenation reaction. We have an example reaction of an alkene reacting with NBS in the presence of lighter heat to form an allylic bromide. We do get a mixture of stereoisomers in this product. Our 3-phrase sentence for this reaction: an alkene plus NBS makes an allylic halide. We need to know that 3-phrase sentence in all possible combinations. We need to be able to say an alkene plus NBS makes an allylic halide. NBS turns an alkene into an allylic halide, and an allylic halide can be made by reacting an alkene with NBS. This reaction works for NBS or its chlorine derivative NCS. We need an alkene in the starting material and that alkene remains in the product, and it goes through a radical intermediate. Some tags for this reaction: this is a regioselective reaction. It forms a most stable carbon radical intermediate, and it forms the most stable alkene product. It is non-stereoselective. It gives a mixture of stereoisomers in our product, and it is a formal oxidation. From the perspective of the allylic carbon starts at the 0 CZ bond oxidation level and ends at the 1 CZ bond oxidation level.
Thanks for training with us today, Ninjas. Check out this other content to see if you can level up even further. As always, don't forget to like and subscribe.